2010 Calculus AB free response question number 5. So let's read the problem first. Before we even read, if you look at the label for the graph that's given, it says the graph of g prime, the graph of the derivative of g. It's very important when you're looking at a problem where a graph is given to understand what graph is given. So in this problem, it is the graph of g prime that's given, because sometimes you'll be asked questions about other functions, but you're looking at the graph of g prime. So it says here the function g, we're given the graph of g prime, but we're getting some information about the function g when we read the first sentence in the problem. The function g is defined and differentiable on the closed interval from -7 to 5 and satisfies g of 0 is 5. The graph of y is equal to g prime, that's the graph that's given. The graph of the derivative of the function g prime, is given, and it consists of a semicircle and 3 line segments as shown in the figure. So part A, find g of 3 and g of -2. So that's why it's important for you to understand what graph you're looking at, because you're not looking at the graph of g, you're looking at the graph of g prime, but you're being asked to find g of 3 and g of -2. So how will you do that? What you have to do is you have to begin by identifying what you know about this problem. What do you know about this problem? You know that g of 0 is equal to 5. That's what you know. What do you want to find? You want to find g of 3 and g of -2. So how will you accomplish that? You're going to use the fundamental theorem of calculus, which states that if you take the definite integral of g prime of x dx from -2 to 0, it will be equal to the antiderivative of the integrand. The antiderivative of g prime would be g, evaluated at the upper limit, minus the antiderivative evaluated at the lower limit of integration. That's the fundamental theorem of calculus. So why do we choose these values for the limits of integration? Because we want to find g of -2, so I'm working on that first, and we know g of 0. Because we know g of 0, we want to have that as one of the limits of integration, so that we'll be able to substitute a value for g of 0. And because we're trying to find g of -2, we want to have that as our other limit of integration, so we can solve for the unknown. So let's go ahead and do that. So that's what we have, and we're going to solve for g of -2. Just add that to both sides of the equation. So we have g of -2. That would be equal to g of 0, which was on the right side of the equation to begin with. But now I have to take this definite integral and subtract it from both sides of the equation, so that it will move from the left side of the equation to the right side of the equation. So I added g of -2 to both sides of the equation to get it on the left side of the equation, and I subtracted the definite integral from both sides of the equation to get it on the right side of the equation. And now I have successfully isolated what I'm solving for, g of -2. It's equal to g of 0, which is given to be 5, minus the definite integral of g prime of x dx from -2 to 0. So I have the minus sign. So the minus sign is carried over here. And how do I find the value of the definite integral of g prime of x dx from -2 to 0? Well, we are given the graph of g prime, so we're going to interpret this definite integral as the area under the graph of g prime from -2 to 0. So here's -2 for x, here's 0 for x, and this definite integral is the area that's under the graph of g prime from -2 to 0. So it's going to be the area of this quarter circle. So how do we find the area of a quarter circle? Well, you find the area of the full circle and multiply by 1/4. So that's what we're going to do now. So how do you find the area of a circle? The area of a circle is pi r squared. So what we have here is the radius of the circle. What is the radius of this circle? The radius of this circle is 2 units. So the area of the quarter circle would be 1/4 of pi r squared. And that's what I have here. 1/4 pi r squared. And 2 squared is 4. 1/4 times 4 is 1. So I just have 5 minus pi for that. And then we also have to find g of 3. How do we find g of 3? Again, we use the fundamental theorem of calculus. Why do we want the limits of integration to be from 0 to 3? We want that because we're given g of 0 and we want to find g of 3. So by the fundamental theorem of calculus, we have g of 3 minus g of 0, and we will solve for g of 3. That's what we're looking for. So g of 3, how can you isolate g of 3 in this equation? Let's look at that. So the way you're going to isolate g of 3 in this equation is just add g of 0 to both sides of the equation. So you have g of 3 isolated, and we made that happen by adding g of 0 to both sides of the equation. So when you add it to the left side of the equation, you'll have g of 0 plus what was there before, plus the definite integral of g prime of x dx from 0 to 3. So what is g of 0? That was given to be 5, so we've got 5 there. And then the definite integral of g prime of x dx from 0 to 3. Well, here's 0, here's 2, and here's 3. So it's going to be the area of the quarter circle plus the area of this triangular region. So the area of the quarter circle we already found in part A. That was pi. So we have 5 plus the area of the quarter circle, which is known to be pi. So we have 5 plus pi. And now we have to find the area of that triangular region. And if you look at the triangular region, you know the base is 1 unit and the height is 3 units. And the area of a triangle is given by 1/2 base times height. So that's going to be 3 halves. So we have 5 plus pi plus 3 halves. 5 plus 3 halves, 5 is 10 halves, plus 3 halves is 13 halves plus pi. So that's how you do part A. So we're using the fundamental theorem of calculus, but most importantly for part A, you've got to understand that you're looking at the graph of g prime, and you're being asked to find g of 3 and g of negative 2. So let's take a look at part B. So in part B, again, in this problem, you're given the graph of g prime. What are we being asked about in part B? Find the x-coordinate of each point of inflection of the graph of g. So you have the graph of g prime. You're being asked to find the x-coordinate of each point of inflection of the graph of g. On the interval from -7 to 5, explain your reasoning. So what is a point of inflection? So let's look here at the definition of point of inflection. It says, let f be a function that is continuous on an open interval, and let c be a point in the interval. If the graph of f has a tangent line at the point, meaning the derivative of the function exists, then this point is a point of inflection of the graph of f if the concavity of f changes from upward to downward or from downward to upward at the point. So you have a point of inflection where the concavity of the graph changes. And the other requirement is that the graph must have a tangent line at that point, which means that the derivative of the function would be defined. So how do you know where the concavity of the graph will change? So to know that, you have to go back to the definition of concavity. And you may be more comfortable with the test for concavity. It comes from the definition of concavity. But in some problems, the reality is it's probably going to be easier for you to determine concavity by knowing the definition rather than the test. They're the same. One is derived from the other. But let's look at the definition of concavity. What do we mean by concavity? Let f be differentiable on an open interval I. Now, when we talk about concavity, it's necessarily for a graph. The graph of f is concave upward on the interval I if the derivative is increasing on the interval, and concave downward on the interval I if the derivative is decreasing on the interval. Now, you may be more comfortable with the test for concavity, but it comes from this definition. Look at the definition of concavity. It says here, the graph is concave upward on an interval I if f prime is increasing on that interval. What does it mean for f prime to be increasing? How do we know if a function is increasing? If its first derivative is positive on an interval, the function is increasing on that interval. But what is the first derivative of f prime? It would be f double prime. F double prime is the first derivative of f prime. The definition of concavity says if f prime is increasing on the interval, which means f double prime is positive on the interval. So if f double prime is positive on an interval, the graph of f is concave upward in the interval. If f double prime is negative on an interval, that means, of course, going back to the definition, f prime is decreasing on the interval, which means f double prime must be negative. The derivative of f prime would be negative because f prime is decreasing. So if f double prime is negative, that means f prime is decreasing and the graph of f is concave downward. And before we go on further with the problem, let's quickly review what this means in terms of concavity. F prime is increasing, so if you have a graph where the derivative is increasing, the slopes of the tangent lines are getting greater and greater. So you'd have something like this. That's what we mean by concave upward, and if you were to draw tangent lines to the graph, if the graph is concave upward, the tangent lines would be below the graph. Sorry for the drawing. Let me see if I can do better here. Okay, so let's say you've got, so you'd have something like that. So the tangent line is below the graph, that means concave upward. And in fact, the slopes of the tangent lines are, if you draw more of them, you can see that as the x values increase, the slopes are also increasing. That's why we have this definition. The graph is concave upward on an interval if the slopes of the tangent lines are increasing on that interval, which means the tangent lines are going to be below the graph. And then if you look at what it means for a graph to be concave downward, so suppose you have a graph that looks something like this. What does it mean that the graph is concave downward? If you look at the definition, it says here f prime is decreasing on that interval. And let's look at a couple of tangent lines to the graph here. So here's one tangent line, and here's another tangent line. So I should make it touch. Here's another tangent line. Okay, there we go. And you can see that the slope of the yellow tangent line, how does it compare to the slope of the green tangent line? Well, the slope of the green tangent line is less than the slope of the yellow tangent line. So that means f prime is decreasing. And that's what we mean by concave down. And you can see that the tangent lines are above the curve, right? So when you have concave downward, the tangent lines are above the curve. When you have concave upward, the tangent lines are below the curve, as we saw earlier. But what you really need is, most of you understand the concept that we just explained in terms of a graph, but you've got to just remember the definition of concavity. And many of you probably remember the theorem, the test for concavity, using the sign of the second derivative. But as I said earlier, sometimes it's easier to do a problem just by remembering the definition of concavity. So look at the problem here. It says find the x-coordinate of each point of inflection. We know a point of inflection occurs where the concavity of the graph changes, as long as there is a tangent line to the graph at that point. And that will happen if the derivative exists. So where do we have changes in concavity? Well, look at the definition for concavity. The graph of a function is concave upward on an interval if the derivative of the function is increasing on the interval. It's very easy for us to determine where the graph of g is concave upward because we're given the graph of its derivative. And if you look at the definition, it says the graph of a function is concave upward on an interval if the first derivative is increasing on that interval. And look at the graph of g so that you can determine where the graph... Did I say look at the graph of g? I meant look at the graph of g prime. Look at the graph of g prime so you can determine where the graph of g is concave upward. So let's look at the graph of g prime to determine where the graph of g is concave upward. By definition, the graph of g will be concave upward on an interval where g prime is increasing. Where is g prime increasing? Just look at the graph of g prime. You can see it's increasing from -7 all the way to 0. The graph is rising from left to right. Where is g prime decreasing? And where that happens, the graph of g will be concave downward. Well, you can see just by looking at the graph of g prime that it's decreasing from 0 to 2. So that's an interval where the graph of g will be concave downward. So we can see that the concavity changed at 0. So at x is equal to 0, we have a point of inflection. So let's look at that here. By definition, the graph of g is concave upward on an interval if the derivative is increasing on that interval, and concave downward on an interval if the derivative is decreasing on that interval. And by definition, we're just referring to the definition to explain, right? Because it says here, explain your reasoning. By definition, the graph of g has a point of inflection at a point P if the concavity of the graph changes at P and the graph of g has a tangent line at P. So where do we have points of inflection? We have a point of inflection at x is equal to 0 because that's where the graph would go from concave upward to concave downward. And we have a point of inflection at x is equal to 2. Because what happens at x is equal to 2? The graph of g would go from, let's take a look here what happens. From 0 to 2, the graph of g prime is decreasing. And if the graph of g prime is decreasing, the graph of g must be concave downward. And if you look at the interval from 2 to 3, the graph of g prime is rising. So g prime is increasing. And if g prime is increasing, the graph of g would be concave upward. So we have at x is equal to 2 a point of inflection because by looking at the graph of g prime and using the definition of concavity, we know that g would be concave downward from 0 to 2 and concave upward from 2 to 3. So we have a change of concavity at x is equal to 2. And similarly, we have another change of concavity at x is equal to 3. Why do we have that? Again, just look at this definition of concavity. We know what we mean by a point of inflection. It's where the concavity changes. But take a look over here. You're looking at the graph of the derivative of the function g, right? And what do we know? If the derivative is increasing on an interval, the graph of the original function is concave upward on the interval. If the derivative is decreasing on an interval, the graph of the original function is concave downward. So take a look over here. The derivative is increasing from 2 to 3, so the graph of g would be concave upward, and The derivative of g is decreasing from 3 to 5, so the graph of g would be concave downward from 3 to 5. So we have a change of concavity at x is equal to 3, so that's another point of inflection. You're going to be doing parts A, B, and C. So we looked at parts A and B together, and I'd like you to give part C a try on your own.